Hey everyone, and welcome back. Looks like we're diving into some seriously brainy stuff today.
Oh yeah, some real head scratchers this time.
Lecture notes on thermal circuits from an advanced heat transfer course. No pressure, right?
Well, no need to panic.
Yeah.
Yeah.
Yeah, I mean, we'll unpack it all, make it nice and digestible for everyone.
Exactly. So basically, thermal circuits are this super clever way to analyze how heat moves around in a system.
Instead of just wrestling with those crazy heat transfer equations directly, huh?
Exactly. It's like we're borrowing the principles of electrical circuits, but for heat.
Wait a second, are we talking about like wiring up a heater to a circuit or something?
No, not quite. It's more about using the concepts and tools we already have for electrical circuits to help us understand heat flow.
Okay, I'm starting to see the light here. So instead of amps and volts, we're dealing with what? BTUs and degrees.
You got it. Think about it. In an electrical circuit, you have resistors, capacitors, and voltage sources, right?
Right.
Well, thermal circuits have their own versions of those.
Ooh, thermal resistors, like those heat sinks on computer chips.
Exactly. Thermal resistance is all about how easily heat can flow through a material. A thick wall would have high thermal resistance, while a thin sheet of metal would have low resistance.
So good insulators, basically like thermal resistor trying to block the heat flow.
Exactly. And then you've got thermal capacitance, which is like the thermal equivalent of a capacitor.
So is that like how much heat a material can store? Like a big brick wall taking forever to heat up, but then holding that heat all night?
You're getting it. Think of it like a thermal battery. Different materials have different abilities to store heat.
So we've got our thermal resistors and capacitors. But how do we actually see how temperatures change over time? Like, is my coffee going to cool down before I finish this episode?
That's where transient analysis comes in. It's like watching a thermal movie instead of just a snapshot.
So we see the temperatures rise and fall as the system does its thing.
Precisely. And for that, we have a secret weapon. Laplace Transforms.
Laplace Transforms. Is this where things start to get a little calculus key?
Well, yes, but no need to get bogged down in the nitty-gritty algebraic details. Just think of Laplace Transforms as a way to make those complex equations much easier to solve.
So like a mathematical shortcut for dealing with all those changing temperatures.
Exactly. And trust me, they make life a whole lot easier when you're analyzing these systems.
Okay, I'm taking your word for it. So with all this fancy math and these thermal circuits, what are some of the real-world benefits we can expect?
Well, for starters, it lets us optimize design.
Yeah, like making sure our phones don't turn into mini ovens, right?
Haha, exactly. But it goes way beyond that. We can use it to design more efficient heat sinks, figure out the best insulation for buildings, even analyze how heat moves through the engine of a car.
From smartphones to spaceships, all thanks to these thermal circuits. Sounds pretty powerful.
It is. But like any tool, it has its limitations. We'll talk about those after the break, so everyone grab a coffee, and we'll be right back. Welcome back, everyone. Now are you ready to put these thermal circuits to the test?
Oh, absolutely. Let's crank up the heat and see what these circuits can really do.
Perfect. So let's say you're designing a brand new smartphone.
Okay.
Sleek, powerful, and definitely not the kind that'll burn a hole in your pocket.
Yeah, those exploding phone stories are not exactly great marketing.
Right. So we want to make sure those components stay cool even under pressure. And that's where thermal circuits come in.
Okay, so how do we start? Do we just like draw a little circuit diagram of the phone?
Pretty much. We begin by identifying the main heat generators. You know, the usual suspects, the processor, the battery,
Right.
and maybe that super fancy new graphics chip you just had to have.
Hey, now phone's got to have a good GPU.
Of course. But each of these components is going to have its own thermal resistance and capacitance.
Right, so we're basically figuring out how much heat each part is pumping out and how good it is at storing it. Right.
Exactly. It's like taking inventory of all the heat sources and their quirks.
Gotcha. But what about the phone's casing? Doesn't that play a role too?
Absolutely. The casing is basically a pathway for heat to escape, so its thermal resistance is super important.
Right, we don't want the heat trapped inside the phone.
Exactly. And we can't forget about the environment outside the phone. The air temperature, airflow.
Oh yeah, even my hand holding the phone.
Exactly. All these factors contribute to how the phone manages heat.
Wow, it's like we're building this intricate thermal map of the whole system.
It is a complete picture of the phone's thermal world.
So once we've mapped everything out, how do we connect the dots? Literally.
Well, we connect all these components using something called thermal resistances, just like wires in an electrical circuit.
Okay, so these connections show how heat flows from one part to another, always looking for the easiest way out, right?
You got it. Heat always wants to take the path of least resistance, just like electricity. So if we want to prevent overheating, we need to make sure those escape routes are nice and clear.
It's like we're designing a thermal escape plan for the heat.
That's a great way to put it. And here's where things get really cool. Remember those shortcuts we talked about earlier? Things like Thevenin's theorem?
Oh yeah, the thermal cheat codes?
Exactly. We can use them to simplify the circuit and make the calculations a whole lot easier.
So less time with complicated equations, more time actually solving the problem.
You got it. It's all about working smarter, not harder.
I can definitely get behind that. But I still have one question. How do we actually solve for those temperatures? I mean, we're talking about real numbers here, right?
Right. We need to know exactly how hot each component is going to get.
And that's where our Laplace Transform buddies come in, right?
Oh, know it. Those Laplace transforms help us analyze those temperatures as they change over time.
So like when I'm playing that super intense game and my phone starts to feel a little toasty.
Haha, exactly. We need to understand not just the final temperature, but how quickly it gets there.
Yeah, a phone that slowly heats up is way better than one that suddenly bursts into flames.
Exactly. We want to avoid those thermal surprises.
This is incredible. By building a thermal circuit and using those Laplace transforms, we can actually predict how the phone is going to behave in the real world.
That's the beauty of this method. We can model those real-world conditions and see how the phone performs under pressure.
So we're not just guessing, we're actually simulating what's going to happen.
Exactly. We're using the power of math to predict the future of our phone's temperature.
This is blowing my mind. From smartphones to spaceships, who knows what we can do with these thermal circuits?
The possibilities are practically limitless. But before we get too carried away, let's remember that this method, like all methods, has its limitations.
Right. It's not a magic bullet, is it?
It's not. It works best under certain conditions, like when heat is flowing in mostly one direction. But what happens if the components have really weird shapes? Or if the temperatures are going haywire inside?
Yeah, our neat little circuit diagram might not be able to handle all that.
Exactly. It's like trying to fit a square peg in a round hole. Sometimes you just need a different tool.
So we need to know when to use thermal circuits and when to maybe try a different approach.
Precisely. But even with those limitations, thermal circuit analysis is an incredibly powerful tool for understanding and managing heat flow.
It's definitely opened my eyes to a whole new way of looking at heat.
It's a fascinating field. And the best part is we're just scratching the surface. There are so many new discoveries and applications just waiting to be explored.
I can't wait to see what the future holds for thermal circuits. This has been an amazing deep dive. Okay, so we've explored these thermal circuits, seen how they work, and even tackled a real-world problem.
We've really put them through their paces.
We have. But now I'm curious, what's next for thermal circuits? Are we talking flying cars powered by perfectly optimized thermal systems?
Haha, while flying cars might be a bit further down the road.
Okay.
But the future of thermal circuit analysis is definitely looking bright.
Bright like a supernova or bright like a heat lamp?
Haha, let's go with supernova on this one. One of the most exciting developments on the horizon is the integration of AI and machine learning into the mix.
AI and thermal circuits. That sounds like a match made in high-tech heaven.
It is. Imagine being able to feed an AI all the data about a complex system, geometry, materials, operating conditions.
Right.
And it spits out a perfectly optimized thermal design, just like that.
So basically the AI becomes like a thermal design guru. Sign me up for those lessons.
Haha, exactly. AI can analyze massive amounts of data way faster than we can, and it can spot patterns that we might miss completely.
So it's like having a thermal super sleuth on the case.
Exactly. And that means we can create even more efficient designs, push the boundaries of what's possible, and all while saving a ton of time and effort.
So no more late nights hunched over equations. The AI will handle that.
Well, hopefully it'll free up some time so we can focus on the bigger picture.
I like the sound of that. But AI isn't the only thing shaking up the thermal world, right? What other advancements are we seeing?
Well, another really exciting area is the application of thermal circuits to increasingly complex systems.
Complex like how?
I'm talking about modeling everything from those tiny microfluidic devices to massive power plants.
Whoa, from the microscopic to the mega. That's a huge leap.
It is, but it requires some serious computational muscle, new algorithms and software that can handle all that complexity.
Right, because those old calculators probably won't cut it.
Not a chance. But the potential benefits are enormous. Just imagine being able to optimize the thermal performance of an entire city. or designing renewable energy systems that are even more efficient.
Wow, from smartphones to cities, that's a pretty impressive range.
It is, and that's what makes this field so exciting. There's always something new to discover, some new challenge to tackle.
Yeah. So it sounds like the future of thermal circuits is all about thinking bigger, pushing the boundaries, and maybe letting AI handle some of the heavy lifting.
Exactly. It's a field that's constantly evolving, and that's what makes it so fascinating.
It's been an incredible journey exploring this world of thermal circuits. We've learned so much about how heat flows, how to model it, and even how AI is changing the game.
It's been a real deep dive into the heart of thermal systems.
It has. And it's shown us just how important understanding heat is for everything from our smartphones to the future of our planet.
Absolutely. Heat is all around us. It shapes our technologies, our environment, and even our own bodies.
It's a fundamental force of nature, and now we have these powerful tools to analyze it and harness its potential.
Exactly. And who knows what amazing discoveries are still waiting to be made.
Well, on that note, we'll leave you with a final thought. Keep those brains buzzing and never stop exploring. Until next time, happy analyzing, everyone.